This brings us to today's last tutorial, cross-validation. So let's briefly look back. What is a good model? We said a model that predicts new data. So what's the idea of validation? You've just seen it in the last tutorial. You train on one data set, and then you get another data set for testing. The problem is you now need to get two data sets. Getting two data sets is often infeasible. Now, we get data often from sources where the data has been collected for another reason. So it's problematic. So now cross-validation is the trick to do so without having to get yet another data set. K-fold cross-validation. What's the motivation? We could have one random split, but that random split could result in biased training test distribution. So if we take the data, we take half of it, call it test, we call the other half, we call it training. Then there will be some difference between the two of them, just by the way we randomly split it up. So here's the data. We could say, we could have a train set in principle that is the higher points, and we could have a test set that's the lower ones, in which case we would be doing incredibly badly on the test set. So we don't want to have situations like that. So what we do is we take every data point and we randomly put it into one of like k folds. Here we use 4 folds. So what I'll be describing is k-fold cross-validation with 4 folds. So where k is 4. All the dark blue points are fold 1, brighter blue, fold 2, yet brighter, fold 3, slightly greenish, fold 4. And then the idea is that we take the data from 3 folds, in this case folds 2, 3, and 4, and we use these data to predict the data in fold 1. And then we train on folds 1, 3, and 4 and predict the data in fold 2. We do the same thing for fold 3 and the same thing for fold 4. So what has just happened? Now, in every case, we use 3/4 of the data, or in other words, k minus 1 over k of the data, to predict the remaining parts of the data. So instead of just having 2 data sets, one where we train, one where we test, now we're in that situation where we always predict things based on the other data. The important thing is, like, if we do cross-validation, we don't have what's called leakage. Leakage is if something from our training set makes it into our test set. So let's go back to cross-validation. So if we had just one random split, it could result in a biased training test distribution. The solution is multiple random splits with k folds. So what are the steps? We define a model to evaluate. For example, say a linear model. Then we take 1 fold of the test set and the rest is the training set. We fit the model with that training set. Estimate the mean squared error on the test set if we have that linear model. Here's our linear model. And then we calculate the mean squared error on the testing mean squared error as the sum over all the tests here of the errors that were made on that corresponding test, where this is our definition of the test set. So if we do k-fold cross-validation, again, here we have our model, then we're going to get the mean squared error on fold 1, the mean squared error on fold 2, mean squared error on fold 3, mean squared error on fold 4, and so on and so forth. In this case, we just have 4. We take all of them, which gives us the averaged mean squared error. Now, so now we have k-fold cross-validation. We repeat the same 4-fold cross-validation for the other pieces, gives us the average one. Now we can do k-fold cross-validation on our polynomial data set, and the average mean squared error will go down, say up to polynomial order 3, and then it's going to go up again. And now the best model is the model that has the best average mean squared error model. Now, the logic of this is just we want it to be good at predicting things that it hasn't seen, but we also want that it basically has seen as much as possible. And leave one out cross-validation is the extreme case instead of that. Instead of leaving a fold out for test, we just make it that each fold is really just a single data point. So we predict every data point based on all the others. This is what we had from k-fold. And for leave one out, we really just take a single data point out. In this case, this one. Use all of them to test the remaining one. I should warn though, there are issues when it comes to the statistical properties of leave one out cross-validation. But it's one that is frequently used by people. And like we do the linear thing, we calculate the mean squared error. For the next point, linear, calculate the mean squared error all the way up to the last one. N times gives us the average mean squared error. It's basically running the cross-validation on all individual pieces. Again, gives us a very similar curve with the best model being polynomial of degree 3. Now in the notebook, you will implement k-fold cross-validation for model selection of polynomial regression. Enjoy.